Imagine this. You're standing on top of a giant concrete platform. It is floating in a quiet Norwegian fjord. The weather is calm. There is no storm, no explosion. Nothing looks dangerous. Engineers are slowly filling the structure with water. That is normal. They need the platform to sink deeper so they can connect the upper deck. Everything is going exactly as planned. And then, bang! A deep sound comes from somewhere inside the concrete. A few seconds later, another bang. The structure starts to shake. Someone hears water rushing into one of the shafts. The pumps are started immediately, but the water is coming too fast. The crew has only minutes to leave, and then, right in front of them, this enormous structure starts disappearing under the surface. Just 18 minutes after the first sign of trouble, Sleipner A is gone. No storm destroyed it, no ship hit it. It failed during a controlled test. And the most frightening part, the computer model said it was safe. Sleipner A was not a normal oil platform. Its base was a huge concrete structure designed to stand on the seabed of the North Sea. Think of it like a giant concrete city under the water. It had 24 large circular cells. Some were used for ballast, some were used for storage, and 4 tall shafts would support the platform above the sea. The whole structure was massive, thousands of tons of concrete, built to survive waves, storms, and pressure for decades. Before the upper deck could be installed, the base had to be lowered deep into the water. So engineers filled the cells with seawater. The more water they added, the deeper the structure sank. Simple. At least that was the idea. But every meter deeper also meant more pressure pushing against the concrete walls. At around 65 meters below the surface, something finally gave way. The first bang was loud enough to get everyone's attention. Then the structure started vibrating. Water was entering one of the main shafts. The crew tried to save it. They started emergency pumps. They tried to remove water faster than it was coming in. But the leak was growing. The platform was getting heavier, and as it sank deeper, the pressure outside became even stronger. That pushed even more water through the damaged area. It was a chain reaction. More water meant more weight. More weight meant deeper water. Deeper water meant more pressure. And more pressure meant even more water. There was no way to stop it. 8 minutes after the first bang, the order came. Abandon the platform. 22 people escaped. Then they watched from nearby boats as one side dropped lower. Then the rest followed. The entire concrete structure sank to the bottom of the fjord. When it hit the seabed, the impact was so strong it was detected like a small earthquake. A project worth hundreds of millions of dollars had disappeared in 18 minutes. At first, investigators had one big question. How could such a massive structure fail so quickly? The answer was hidden in a very small part of the design. The large cells were round. But when 3 round cells touched each other, they left a small triangular space between them. That space was filled with reinforced concrete. These parts were called tricells. Compared to the rest of the platform, they looked almost unimportant, but they had a difficult job. They connected the large cells and carried huge forces between them. And unlike the round walls, the tricells had sharp corners and complicated shapes. That is exactly where stress can build up. As the platform sank deeper, water pressure pushed harder and harder against those areas, and one of them was much weaker than the engineers believed. The structure had been tested using finite element analysis. That sounds complicated, but the basic idea is simple. The computer takes one huge structure and divides it into thousands of small pieces. Then it calculates how each piece should react to pressure. Where will it bend? Where will it crack? Where will the highest forces appear? It is a powerful tool, but there is one problem. The computer only understands the model you give it. And the model of the tricell area was not detailed enough. It underestimated the real forces by almost half. Almost half! So on the computer screen, the design looked safe, the numbers looked clean, the colorful stress diagrams looked convincing, but inside the real structure, the forces were much higher. The concrete had less strength than the model predicted, and there was not enough reinforcement in the exact place where it was needed. The computer did not make a random mistake, it gave a very precise answer to a bad model. And that made the result dangerous, because a believable wrong answer is often worse than no answer at all. So at around 65 meters deep, the pressure became too much. A tricell wall failed, a large crack opened, water rushed inside. And once that started, the whole platform was in trouble. The pumps were not designed for a hole like this. They could handle normal ballast operations, maybe a small leak, but not a major structural failure. The structure became heavier every second, it sank faster, the pressure increased, the crack allowed even more water in. At that point, the platform was no longer being controlled by engineers. It was being controlled by gravity and water pressure, and those two forces do not negotiate. After the accident, investigators created a better computer model. This time, they used a much more detailed mesh around the tricells, and the result was shocking. The new model predicted failure at almost the exact depth where Sleipner A had actually failed. The physics had always been there. The real structure had behaved exactly as it should. The problem was that the first model did not show it. That is what makes this disaster so important. The platform was not destroyed by some strange force nobody understood. It was destroyed by a weakness that could have been found. The warning was hidden inside the calculations, but nobody saw it, or maybe nobody questioned the model hard enough. The Sleipner project did not end there. A replacement platform was built, the weak areas were redesigned. The tricells received stronger reinforcement, the calculations were checked more carefully, and the new platform was eventually installed successfully. But the original Sleipner A was left at the bottom of the fjord, a huge broken structure. A reminder that computers do not remove human responsibility. A simulation can look advanced, it can produce perfect numbers, it can give engineers confidence, but it cannot tell you whether you ask the right question. Sleipner A was designed to survive the North Sea for decades. Instead, it disappeared during a calm test in just 18 minutes. It was built to carry enormous weight. In the end, it was brought down by something much smaller, a hidden weakness. The model looked correct, the numbers looked correct. The platform did not care. That is the part of failure we are interested in here. Not only the moment everything falls apart, but the moment it first starts going wrong. Subscribe to Failure Atlas for more stories like this, and tell me in the comments, where should we go next? Thank you for watching, and see you in the next video.